It was 40 years ago that I still remember the day. It was the first class after lunch, sophomore English. I'd gotten there early, like I usually did, just sitting at my desk, waiting for the room to fill. Students trickled in, dropping backpacks, talking about nothing in particular. Then one of the class clowns walked through the door, louder than the rest, proclaiming that you wouldn't believe it, but the space shuttle had blown up. He joked about everything, so I didn't know whether to believe him. There was no announcement, no teachers rushing in, just the normal shuffle of a school day and a rumor hanging in the air. Class went on as if nothing had happened, but by then whispers had started. You could see it on the TVs outside the cafeteria. When the bell rang, I changed my usual route. I walked toward the cafeteria, and that's where I saw them. Two small TVs on carts in the lobby, both playing the same thing on a loop. The launch, the blue Florida sky, the bright plume, and then that shape in the air where the shuttle was supposed to be. The footage played on a loop. Launch, climb, flash, smoke. Again, launch, climb, flash, smoke, over and over. No one thought to turn it off. No one considered what it meant to watch people die repeatedly in a school hallway between classes. There was no plan for this. The 1980s hadn't prepared us for tragedy broadcast live into our schools. No counselors appeared, no announcements were made, just teenagers standing in silence, watching the same 73 seconds and the same way again and again. I had followed Christa McAuliffe's story, the teacher in space, the idea that an ordinary person could ride a shuttle into orbit and talk to students from the stars. It left a knot in my stomach that never quite went away. 40 years later, it still brings tears to my eyes. This is the story of that day.
Across the United States, classrooms prepare for something extraordinary. Televisions are rolled in on carts. Students sit cross-legged on linoleum floors, eyes fixed on flickering screens. Teachers stand at the back of the room, smiling with quiet pride. One of their own is going to space. Sharon Christa McAuliffe, 37 years old, social studies teacher from Concord High School in New Hampshire. Wife, mother of two. She had been chosen from 11,000 applicants to represent teachers everywhere, to show that space wasn't just for astronauts anymore, but for ordinary people with extraordinary dreams. She had told her students, "I touch the future. I teach." The process had been long. Applications, interviews, evaluations, background checks. Each step narrowed the field. Christa remembers filling out forms at her kitchen table late at night. She remembers telling her students that even if she wasn't chosen, the act of trying mattered, that courage was part of learning, that exploration wasn't reserved for a select few. When the phone call came, it didn't feel real. She had been selected. Training followed quickly. Suddenly, she was inside simulators instead of classrooms, learning procedures, memorizing checklists, floating during brief moments of weightlessness on training flights, sitting shoulder to shoulder with astronauts who had trained for years to be here. She works hard to earn her place, not as a passenger, but as a crew member. The launch was supposed to happen days earlier, January 22nd, then the 23rd, then the 24th. Each time something intervenes: weather, technical concerns, a problem with a hatch access, crosswinds at the emergency landing site in Africa. The calendar keeps slipping. For the crew, the delays are both frustrating and familiar. This is part of spaceflight: waiting, rechecking, waiting again. But this mission carries unusual weight. The whole country is watching. Children are waiting in classrooms. Christa's students have been counting down for weeks. Greg Jarvis knows the frustration better than most. He's been bumped from mission after mission, reassigned, delayed. This is finally his chance. He's an engineer. He understands the reasons, but understanding doesn't make the waiting easier. Each morning, the crew goes through the same preparation rituals, not knowing if today will be the day. Commander Dick Scobie reviews flight procedures and abort scenarios. As commander, his responsibility extends beyond flying. He must be ready to make split-second decisions for the entire crew. He studies weather patterns, trajectory data, backup plans. His training is about command authority as much as technical skill. Pilot Mike Smith focuses on different details. He'll be managing systems, monitoring instruments, backing up every decision Scobie makes. For a pilot, preparation means chair flying, mentally rehearsing every switch throw, every gauge reading, every procedure from memory. This is his first spaceflight. He's thought about this moment for years. Now he runs through it again and again in his mind. The mission specialists have their own preparations. Judy Resnick checks her experimental equipment. She'll be operating the shuttle's robotic arm. Ron McNair reviews the satellite deployment procedures. Ellison Onizuka goes over his assigned tasks methodically, the way he approaches everything. Christa rehearses her lessons. She has cameras to operate, experiments to conduct, students to reach. She practices in the simulator, learning where everything is located, how to move in the tight space, how to speak clearly while floating. Each delay means running through it all again. By January 27th, the frustration is palpable. Another scrub, this time because of high crosswinds and a problem with the exterior access hatch. Families who have flown in for the launch make uncertain plans. Do they stay another day? How many more delays can there be? That evening, the temperature begins to drop. Forecasters predict overnight lows in the 20s, unprecedented for Cape Canaveral. Engineers raise concerns about cold weather and its effects on seals, on systems designed for Florida's warmth. Discussions continue late into the night. But by morning, the decision has been made. January 28th, the launch will proceed.
The morning is colder than anyone expected. At Cape Canaveral, the air carries an unfamiliar bite. Frost clings lightly to metal railings and concrete edges, something rarely seen this close to the Florida coast. The wind is still. The sky is wide, cloudless and calm, stretching blue from horizon to horizon. On launch pad 39B, the Space Shuttle Challenger waits. Floodlights fade as daylight takes over, revealing the familiar white shape standing upright against the sky. Vapor drifts from the shuttle's side, curling slowly into the air like breath on a winter morning. Icicles hang from the service structure, beautiful and unnerving at once. This launch has been delayed before. Technical issues, weather, mounting frustration. But today, finally, the countdown continues. On launch morning, the crew suits up quietly. The room is filled with soft sounds, zippers closing, gloves being secured, radios crackling with routine instructions. Each crew member moves with practiced efficiency. Christa smiles for the cameras, but her focus is clear. This is no longer abstract. This is real. The ride to the launch pad is short. As the shuttle comes into view, it dominates the landscape. Metal towers rise beside it. Cables stretch outward like veins. The vehicle is massive, larger up close than it ever appears on television.
Inside the shuttle, the cabin is tight and functional. The crew straps in, lying on their backs, facing the sky they will soon enter. Christa settles into her seat, checklist in hand. Her voice is steady when she responds to calls from the ground. Every sound, the clicks, the hum of systems, the faint vibration, feels amplified. Dick Scobie runs through final checks with calm authority. Mike Smith confirms readouts. Judy Resnick adjusts her headset. Ron McNair exchanges a quiet word with Ellison on his Zuka. Greg Jarvis breathes steadily, waiting. Christa gazes at the mission patch on her sleeve. Outside, spectators gather. Families, NASA employees, journalists, school children on field trips. Christa's parents stand in the crowd, bundled against the cold, pride and anxiety mingling on their faces. Some have waded through previous delays. Today, at last, the moment has arrived. In control rooms, engineers sit before glowing screens. Rows of data scroll past. Voices remain even, professional. This is a place built on discipline and routine, where emotion is kept carefully in check. The final seconds arrive. 10, 9, 8. The crowd grows quiet. 7, 6. Inside the shuttle, the crew listens to the steady cadence in their headsets. 5, 4, 3, 2, 1. Ignition. A thunderous roar erupts beneath Challenger. Fire and smoke burst outward, shaking the ground. The shuttle strains against the hold-down bolts, then rises, slowly at first, almost reluctantly, before committing fully to the climb. Cheers erupt. At the Cape, families scream with joy. In classrooms across the country, children clap and jump. Teachers smile, some with tears of joy in their eyes. The shuttle clears the tower, climbing higher, leaving behind a bright white trail against the impossibly blue sky. It is beautiful. The vehicle accelerates. The sound fades with distance. Cameras track the ascent as Challenger grows smaller, climbing toward orbit. Inside Mission Control, voices call out updates in measured tones. Roll program. Challenger, go at throttle up. Mike Smith's voice comes back, calm and professional. Roger, go at throttle up. The shuttle continues its climb. Vapor trails stream behind it. Everything appears normal. Everything appears perfect. 73 seconds after liftoff. A flash. The shape of the shuttle vanishes in an instant, replaced by a spreading cloud of fire and smoke. The solid rocket boosters spiral away wildly, their trails twisting and branching. Pieces arc outward, carried by momentum alone, falling toward the Atlantic far below. The roar stops. The cheers die instantly. For a moment, no one understands what they're seeing. Eyes remain fixed on the sky, waiting for the shuttle to emerge from the smoke, waiting for some sign that this is a staging separation, a normal event, anything but what it appears to be. It doesn't emerge. White trails drift and curl, forming a branching pattern, a terrible Y shape that hangs in the air far too long. Debris falls. In Mission Control, voices falter. Data streams disappear. Screens show numbers that no longer make sense. Controllers stare at their monitors, hands frozen above keyboards, trying to process information that tells them the impossible has happened. At the Cape, a quiet voice breaks the silence over the loudspeakers. Flight controllers here looking very carefully at the situation. Obviously, a major malfunction. The words hang in the cold air. In the viewing stands, Christa's parents stand motionless, hands clasped together, staring upward. Around them, people begin to cry. Children ask questions their parents cannot answer. In classrooms across America, teachers stand frozen. Some reach forward to turn off the television but cannot move. Others stare at the screen, watching the loop begin again, the launch, the climb, the flash, the smoke. Students look up at their teachers, confused, waiting for reassurance that never comes. The footage plays again, and again, and again. 7 lives are lost above the Atlantic Ocean. Astronauts, scientists, engineers, a teacher. The sky slowly clears. Smoke thins.
the blue returns. But something fundamental has changed. What was once routine is now unthinkable. Confidence gives way to shock. Celebration turns to grief. Ships are dispatched into the debris field. Newscasters break into tears on live television. Families are escorted quietly away from the viewing stands. In Washington, the president prepares to address a grieving nation.
While the world watched press conferences and presidents searched for the right words, I just remember those 10 minutes between classes, staring at a screen in a school hallway, watching the same plume of smoke, the same branching trail in the sky over and over, knowing that somewhere in that fire and cloud were the 7 people we had been cheering for, including a teacher who was supposed to talk to students from orbit. For us, it wasn't just a news story. It was the first time many of us understood, in a way we never had before, that not every dream survives the launch, that courage and tragedy can share the same sky, that the distance between hope and heartbreak can be measured in 73 seconds. 40 years later, we remember Francis Scobie, Michael Smith, Ellison Onizuka, Judith Resnick, Ronald McNair, Gregory Jarvis, and Christa McAuliffe, not for the way their mission ended, but for the courage it took to begin. They reached for the stars. They believed in exploration, in education, in the future. They are remembered. They are honored. They are not forgotten.
In Part 1, we remembered the crew of Challenger and witnessed the tragedy as it unfolded on January 28, 1986. Now we must understand what went wrong and why it matters 40 years later. This is not about blame, it's about clarity, because the only way to honor those 7 lives is to learn from what took them. The Space Shuttle was designed to be reusable. Unlike previous spacecraft that burned up on re-entry or sank into the ocean, the shuttle would land like an airplane and fly again. This required an innovative design. The orbiter mounted alongside a massive external fuel tank with 2 solid rocket boosters strapped to the sides. Those solid rocket boosters, the SRBs, were the largest ever built. Each stood over 149 feet tall and generated 3.3 million pounds of thrust. They were so large they couldn't be manufactured in one piece. Instead, they were built in segments and assembled at the launch site. The segments were joined together using field joints, essentially giant metal sleeves that fit over the seam where 2 sections met. To prevent hot gases from escaping during launch, each joint was sealed with 2 rubber O-rings. Think of an O-ring like a gasket. When you tighten the lid on a pressure cooker, a rubber seal compresses to prevent steam from escaping. The O-rings in the shuttle's boosters worked the same way. When pressure built up during ignition, the rings were supposed to compress and seal the gap. But rubber behaves differently at different temperatures. When rubber gets cold, it becomes stiff. It loses elasticity. A rubber band kept in a freezer doesn't stretch the same way as one kept at room temperature. The O-rings were made of a synthetic rubber compound designed to remain flexible, but their performance degraded significantly below 53 degrees Fahrenheit. On the morning of January 28, 1986, the temperature at the launch pad was 36 degrees. Engineers at Morton Ficol, the company that manufactured the solid rocket boosters, had tracked O-ring performance on previous flights. They had seen evidence of erosion and blow-by, hot gases getting past the primary O-ring on several missions. They had noticed a correlation. Cold weather made the problem worse. The night before the launch, Ficol engineers recommended against launching below 53 degrees. They presented data.
they expressed concern, but under pressure to justify the delay with absolute proof of failure rather than evidence of risk, they reversed their recommendation. The launch proceeded. At ignition, the right solid rocket booster's aft field joint failed to seal properly. The cold O-rings didn't compress fast enough. Hot gases, burning at nearly 6,000 degrees Fahrenheit, began leaking through the joint. For the first few seconds, aluminum oxide particulates from the burning propellant temporarily plugged the gap, acting like a makeshift seal. But as the shuttle climbed and experienced aerodynamic stress, that temporary plug broke free. At 58 seconds after launch, a plume of flame became visible on the side of the right booster. The flame acted like a blowtorch directed at two critical points: the lower strut that attached the booster to the external tank and the external tank itself. The tank held over 500,000 gallons of liquid hydrogen and liquid oxygen, the shuttle's fuel. At 73 seconds, the lower strut failed. The booster rotated and its nose pierced the external tank. The hydrogen tank ruptured. Milliseconds later, the oxygen tank failed. The two propellants mixed and ignited. The shuttle didn't explode, it disintegrated. The orbiter broke apart from aerodynamic forces as the vehicle came apart around it. The crew cabin remained intact initially, separating from the disintegrating shuttle and continuing upward on a ballistic trajectory before falling back into the Atlantic Ocean. The failure began with a seal, a rubber ring less than half an inch thick. In cold temperatures, it couldn't do its job, and once the hot gases found a path through, the destruction became inevitable. The Rogers Commission, the presidential investigation into the disaster, identified failures at multiple levels. But the lessons extend far beyond NASA and far beyond 1986. Technical lesson: environmental limits are not suggestions. Every material has operating limits. Rubber has a temperature range, steel has a fatigue life, concrete has a load capacity. These aren't approximations, they're physical properties. The O-rings had been tested, and their performance below 53 degrees was known to be degraded. But because previous cold weather launches had succeeded despite O-ring erosion, the risk began to feel acceptable. This is called normalization of deviance. When a system survives repeated exposure to a flaw, that flaw starts to feel normal. Engineers stop seeing it as a failure and start seeing it as a characteristic. The lesson: a component operating outside its designed parameters is not performing differently, it's failing slowly. Survival is not the same as safety. This lesson applies everywhere. In aviation, material fatigue limits exist for a reason. In medicine, drug dosages have ranges. In civil engineering, load calculations include safety margins. Those limits aren't conservative estimates, they're the boundary between function and failure.
Human lesson: proving danger is not the same as ensuring safety. The night before the launch, Thiokol engineers were asked to prove the shuttle would fail, rather than being asked to prove it was safe to launch. This reversed the burden of proof. In most engineering decisions, the default position is caution. You don't fly until you've demonstrated it's safe to fly. You don't operate until you've confirmed the system is ready. But schedule pressure, public expectation, and the desire to maintain flight tempo shifted the question. Instead of, can we prove it's safe, the question became, can you prove it will fail? When you can't definitively prove catastrophic failure will occur on this specific launch, the answer is almost always no, and so the launch proceeded. The lesson: risk assessment must start from a position of caution, not optimism. The question should never be, can you prove this will fail, but rather, can you prove this will succeed? This principle appears across industries. In pharmaceutical trials, the burden is on proving safety before approval. In aviation, certification requires demonstrated reliability. In structural engineering, proof testing confirms capacity.
When that burden reverses, when the default becomes proceed unless proven dangerous, risk becomes invisible until it's catastrophic. Organizational lesson. Engineers must be heard. The engineers at Morton Fiacol presented their concerns clearly. They had data, they had experience, they had professional judgment shaped by years of working with these systems. Their recommendation was overruled, not because their data was wrong, but because the institutional pressure to launch was stronger than the institutional willingness to delay. In complex systems, the people closest to the hardware often see problems first. They notice anomalies, they track trends, they recognize when something is behaving differently than expected. If those voices are not heard, or worse, if they are discouraged from speaking, critical warnings disappear into bureaucracy. The lesson: technical judgment must have authority that matches its responsibility. The people who understand the system must have the power to stop it. This lesson resonates in medicine, where nurses and technicians may spot problems before doctors, in aviation, where maintenance crews flag concerns, in software, where testers identify vulnerabilities. Hierarchy should not silence expertise. After Challenger, NASA grounded the shuttle fleet for nearly 3 years. Investigations were conducted, designs were reviewed, procedures were rewritten. Physical and design changes. The solid rocket booster joints were completely redesigned. The field joints were strengthened with additional metal reinforcement. A third O-ring was added for redundancy. Heaters were installed to maintain seal temperature in cold weather. Joints were tested extensively under various conditions before return to flight. The external tank was modified to reduce the shedding of foam insulation, a separate issue that would later contribute to the Columbia disaster in 2003, proving that even thorough redesigns cannot eliminate all risks. Launch commit criteria, the specific conditions that must be met before a launch can proceed, were made more conservative and more explicit. Temperature limits were established and enforced. Environmental conditions were monitored more rigorously. Procedural and decision-making changes. NASA restructured its decision-making process for launches. The authority to delay or scrub a launch was clarified and strengthened. Engineers were given clearer pathways to raise concerns without requiring absolute proof of failure. Flight readiness reviews became more formal and more thorough. Dissenting opinions were required to be documented and addressed, not dismissed. The concept of launch pressure was acknowledged openly. Schedules were recognized as influencing factors in decision-making, and systems were put in place to counteract that pressure. Evaluation and oversight changes. An independent oversight process was established. Outside review boards were given authority to examine NASA's procedures and decisions. The goal was to prevent institutional groupthink, the tendency for organizations to reinforce their own assumptions without external challenge. Communication between contractors and NASA was restructured to ensure technical concerns reached decision-makers. The line between engineering judgment and management discretion was made clearer. Modern context. Today, spaceflight is entering a new era. Commercial companies are launching humans to orbit. Flight rates are increasing. Reusability is becoming standard. The pressures that existed in 1986, schedule demands, public expectation, the desire to make spaceflight routine, exist again in different forms. The changes made after Challenger remain in place at NASA. Lessons about O-ring behavior, field joint design, and temperature limits are now standard knowledge. But the broader lessons about normalization of deviance, about burden of proof, about listening to engineers must be actively maintained. Systems don't stay safe by accident. They stay safe because people choose caution over convenience every single time.
40 years after Challenger, we remember 7 people who believed in exploration. Francis Richard Scobie, commander, Air Force pilot and aerospace engineer, husband, father of 2. He had logged over 6,000 flight hours and dreamed of flying since childhood. Michael John Smith, pilot,
Navy aviator and test pilot, husband, father of 3. He wanted to see Earth from space just once. Judith Arlene Resnick, mission specialist, electrical engineer with a doctorate from the University of Maryland. She had been the second American woman in space, a pioneer in every sense. Ellison Shoji Onizuka, mission specialist, Air Force officer and aerospace engineer, husband, father of 2. He had been the first Asian American in space and carried the hopes of his community. Ronald Irvin McNair, mission specialist, physicist with a doctorate from MIT, husband, father of 2. He grew up in the segregated South and became one of the few black astronauts in NASA's history. Gregory Bruce Jarvis, payload specialist, electrical engineer and Air Force officer. He had waited years for this flight, bumped from earlier missions, finally getting his chance. Sharon Christa McAuliffe, teacher in space, social studies teacher from Concord High School, wife, mother of 2, chosen from 11,000 applicants to represent teachers everywhere. She told her students, "I touch the future. I teach." Their families still carry the weight of that January morning. Their communities still feel the loss, but their legacy is not only grief. It is the changes that followed, the redesigned joints, the stricter procedures, the clearer lines of authority, the recognition that schedule pressure can silence safety concerns, the understanding that survival is not the same as success. Every launch since Challenger has been shaped by what we learned that day. Every engineer who questions a decision, every manager who delays a launch, every system designed with redundancy and caution, they are part of that legacy. We continue to explore. We continue to reach for what lies beyond our world, but we do so with the knowledge that space is not routine, that risk is never fully eliminated, and that every decision to launch must be made with the full weight of what we've learned. The crew of Challenger reached for the stars. We honor them by remembering not only their courage, but the lessons their loss taught us, and by carrying those lessons forward every time we choose safety over schedule, evidence over assumption, and caution over confidence. They are remembered, they are honored, and the sky they believed in is still worth reaching for, carefully, humbly, and with the respect their memory demands.